this is all fine, but where did those densities come from? How did I know a granite might be 2.7, a diorite might be about 2.1, so on? Well, some of these are actual measurements on rocks, of course, but it's actually pretty hard to get an accurate density out of a rock. A lot of granites, they're a little bit altered, so their densities are going to be lower. Maybe they've got some extra porosity in there from the expansion of the rock, so maybe the density is a little bit lower. One way that we approach this is to actually consider the mineralogy of the rock and then figure out the constituent densities of the different minerals and then add them in proportionally to calculate what the overall density is going to be. Okay, so let's, for example, try and figure out the density on a granite. Row on that. And what kind of granite do we want to have? Okay, let's say we have a granite that is 30% quartz, 30% plagioclase. Okay, not just any plagioclase, you've got to come up with a composition because density depends on composition. Let's call that AN20 plagioclase. Let's see what else is in a granite. K feldspar, so let's do 30% K feldspar, and then the rest of it is going to be some mafic phase. So 10%, and then what we have, biotite or hornblende. Those are fairly typical mafic phases. Okay, so if we know the density of quartz, density of plagioclase, density of K feldspar, density of biotite or hornblende, we could add all these up proportionally and we could figure out the density, right? Well, where do those densities come from? Well, density of quartz is given by what? The mass per mole. Okay, so we want the mass per mole of SiO2 divided by the volume per mole. Okay, this is volume per mole SiO2, and that will give us a density. Okay, so what is that? Well, the mass of SiO2 is 60.08 grams per mole. The volume of quartz in the quartz structure, right? Can't be some other structure. Can't be coesite structure. Can't be stishovite structure. Can't be cristobalite structure. We're talking quartz, actually alpha quartz. And the volume for that is 22.69 centimeters cubed per mole. Okay? Do this 60.08 divided by 22.69, you get 2.65 grams per centimeter cubed. Okay? That's the density of quartz. We can do the same thing for albite. That one is 262.2 grams per mole divided by 100.07 centimeters cubed per mole. You could probably do the math in your head. It's about 2.62 grams per cubic centimeter, right? If we look at anorthite, row anorthite, that's equal to 278.2 grams per mole divided by 100.8 centimeters cubed per mole. Okay, and that is equal to 2.76 grams per cubic centimeter, right? And so here we've got quartz. That's the quartz that we need. We need AN20 plagioclase, so we would take this times 0.8 and this times 0.2, 20% anorthite, 80% albite, and you end up with a density that turns out to be 2.65 grams per cubic centimeter. It turns out to be the same as the density of quartz, fortuitously so. All right, and then we can do K feldspar. Row K feldspar will spare you. That's about 2.57 grams per centimeter cubed. Depends on how much sodium is in the K feldspar. I put in 20% sodium, 80% potassium. Rho on biotite is about 3.05 grams per cubic centimeter, and the density on hornblende is about 3.3 grams per cubic centimeter. Kind of depends a little on what kind of hornblende we're talking about. Okay, so then you'd want to take 30% of this plus 30% of this plus 30% of this, and then 10% of either biotite or hornblende. Okay, so I'm going to erase the board and we're going to go on from here. So just to remind you, row quartz 2.65, row plagioclase AN20 2.65, row K feldspar 2.57, row biotite 3.05, row hornblende 3.30. Okay, so those were the densities that we calculated before. So if I take 0.3 times 2.65 plus 0.3 times 2.65, that's quartz, that's plagioclase, plus 0.3 times 2.57 plus 0.1 times 3.05, I get a density that is about 2.7 grams per cubic centimeter. Okay, a little bit higher than the quartzo-feldspathic minerals, right? Because biotite is heavier. So this is a biotite granite. And if I look at a hornblende granite, you can go through and do all the calculations. Turns out it's about the same. I mean, it's about 2.7 grams per centimeter cube. So why do we think granites have densities that are about 2.7 grams per cubic centimeter? It's because that's what the mineralogy of a granite is made of. Now, you might say, look, Matt, the pressure is going up in the crust, right? And minerals do have some compressibility to them, right? So doesn't everything get a little bit denser as we go down in the crust? Well, it's true, there is compressibility, and it will increase the densities by a little bit, a percent or two as we go from the top of the crust to the base of the crust. But don't forget the temperature is going up also, and minerals also have a very small thermal expansivity. So if I increase the temperature, the densities go down by a little bit. And it turns out that for the geotherms that we typically see in the crust, those two processes cancel, and so the density that you calculate for a granite based on like surface measurements of densities is going to be pretty similar to the density that you calculate as you go downward in the crust. So our last little calculation that I want to do is what is rho on a diorite? And here we're going to assume something really simple. We'll just say it's 50% hornblende and 50% plagioclase. But remember, plagioclase in a diorite is going to have more of an anorthite content. So let's just give it an AN50 composition. 50% anorthite, 50% albite. And so this one is fairly straightforward. Rho on a diorite is about 0.5 times, what did we say our density on hornblende was? About 3.3 grams per cubic centimeter. Density on AN50 plagioclase is about 2.65 grams per cubic centimeter. And so you get a rho on a diorite that's about 3.05 grams per cubic centimeter. Okay, and the last thing is, okay, that's all well and good for the crust. Of course, if you go up to granulite with some orthopyroxene in it, it'll be a little bit denser, maybe 3.1 grams per cubic centimeter. Well, once you get through the crust, you get into the mantle. What's the density of the mantle? We could go through the whole calculation again. Pick your favorite composition of peridotite, the approximate proportions of olivine, orthopyroxene, clinopyroxene, and whatever aluminous phase you have in there. And you would just go through the calculations in the same way. But generally speaking, when people do this, density of a peridotite, typical peridotite, is about 3.3 grams per cubic centimeter. Okay. So if you think about the kinds of materials that we see from the top of the crust down into the mantle, we're looking at density ranges from about 2.7 for a granite to maybe 3.1 towards the base of the crust, and then there'll be a jump to a higher density as you get into the mantle, like 3.3 grams per cubic centimeter. And then just to remind you, 3.3 grams per cubic centimeter is 3,300 kilograms per meter cubed, and of course those are the numbers that you really want for calculating pressures.